Historically, let's say in a mortgage company, the mean time to process a loan request has been about 44 minutes with a standard deviation of 3 minutes, and we don't know if the population is normally distributed or not. So they want to be able to process these faster. By the way, who's the most isolated individual in the mortgage company? That's right, it would be a loan officer. A loan officer. Okay, so there's this new software access system that claims to shorten the time that it takes to process these loans. So the old mean we knew to be this and the standard deviation to be that. And the new mean, here's the deal. What we're going to say is we're going to come up with this distribution. We're going to take a sample, and it needs to be a sample that's more than 30. So suppose we're going to take a sample of size 36. That's going to give us the standard deviation of the means of the old standard deviation divided by the radical of the sample size. So 3 over 6 is 0.5. So what we're going to do is we're going to say, okay, let's assume that this is true, that, that the new software isn't going to make a difference at all. So let's assume that for a second, and that this distribution of sample means, where theoretically these would be infinitely many sample means just due to random chance fluctuation, and how they would be distributed about the true mean of 44. So we're going to take this sample of 36 from this new company. Now, if our sample mean from this new company is way down here, then we would conclude, you know what? This mean we got does not behave like the kind of mean times we'd get to process a loan if it was the old cruddy system that we were using. So if one time we take a sample and our sample mean is like this for the new system, then it's not behaving like the old mean of 44. We would tend to believe that the new system would have a mean average down here somewhere. So somebody's claimed that the new system would give us a mean time of less than 44 minutes would be substantiated if the one mean we took does not behave like the typical means we saw before. However, if the one mean we took gave us a result back over in here, on the other hand, we would say, you know what? We would say that that's not behaving like anything out of the ordinary. Even though that one sample mean was a little bit below 44, it's not unusual enough for us to buy the argument that the new software is taking less than 44 minutes on average to process the loans. So that's the big idea behind hypothesis testing. Well, let's get more formal with it. We're going to write the claim down. So the claim was, somebody said, well, the new mean would be less than 44. Then we're going to write down the complement of that. So the complement of that would be, if that's not true, what is true? And it would be that the mean is greater than or equal to 44. And then whichever one of these statements has the condition of equality, which is this one, this is the one that says the mean can equal 44. In fact, a lot of times we'll just write it like that and not include the greater than, because we're only interested in, is the new mean still the same as it was, or is it less than what it was? So we write down the claim symbolically and then the complement of it. One of those is true, one of those is false. Okay, now, the one that has the condition of equality will become the null hypothesis. So this guy is going to be the null hypothesis. The alternative hypothesis is going to be the other statement, the statement that doesn't include the condition of equality. Now, the reason we need the null to have the condition of equality is because of this. We're going to need a sampling distribution of means to base our decision upon, because that's why we've been studying probability, involving how likely or unlikely is it to get a certain mean average when we take a certain sample. So we're going to say, okay, we're going to assume the null is true, and the null said that the mean was equal to 44. So we're going to build this sampling distribution where the mean is 44. And then we're going to say, oh, okay, well now we'll go take our one sample, and if it behaves like this, like it should, if the null is true, then there's no reason to reject the null. But if it doesn't, if it's down here, we're going to reject the null. So what we do, it ends up looking like this. We have the null hypothesis, we have the alternative, and here's what we set up. We said, okay, this is what should be true. These are how the sample means should be distributed if the null is true. So it's kind of like a court of law. You're innocent until proven guilty. You assume the null is true unless there's enough evidence to get you to believe that the alternative is true. Now, what do we mean by enough evidence to convince us? I'm glad you asked. So by golly, you would have to take a sample and get a mean average that's down here, far enough below the mean in terms of standard deviations, so that it's the type of result that should happen 5% or less of the time when any sample mean is taken from this population with a mean of 44. That's what it takes to be unusual. That's like in a court of law, beyond a reasonable doubt. It has to be something that occurs less than 5% of the time. Now we could use inverse normal to find that z-score that would be right at the place where anything beyond that would happen less than 5% of the time. So this is the z-score that traps 5%. So what we're saying is that for you to be able to reject the null and have enough evidence to go with the alternative, you better be getting a sample mean that's at least that many standard deviations to the left of the assumed mean from the null. Otherwise, you don't have a strong enough case to convince us that the true mean would be less than 44. So let's suppose that this new software, we took a sample of 36 and we got this mean average right here. Is that extreme enough to put us in the critical region and give us enough evidence to suggest that the alternative is true? And we'd give it the check mark and say, yep, we believe that's true. So here's what we do. We say, well, where is this sample mean in this sampling distribution of means? Well, we're going to take the sample mean we get minus the mean of all the sample means divided by the standard deviation of all the sample means, which, if you recall, is going to be sigma over the square root of the sample size, radical n. So what we've got here is we're going to say, okay, our sample mean was 42.8, somewhere down here to the left, minus the mean divided by the standard deviation, which the original standard deviation one score at a time was 3, but we're going to divide that by radical 36. Now what we end up getting is a z-score of negative 2.4. So if you recall, the critical region, which has a critical z-score of negative 1.64 or 5, when we see these z stars, it's the critical z-score that as long as you exceed that, that's enough evidence to suggest we should reject the null. We did exceed that. We have an unusual result. That is not at all a typical kind of a mean, sample mean, one time, coming from a population where the null is true and the mean is 44. So this guy has 2.4 standard deviations below the mean. It is down here, and so our conclusion is we would reject the null in favor of the alternative. Now, we're going to formalize this a little bit more. Once we get that z-score of negative 2.4, we want to calculate something called a p-value. We want to know if the null was true, how often should you get a result at least as extreme as the one we got? This is where the conditional probability came in. What's the probability that you would get a sample mean less than 42.8 given that the null is true? It's a conditional probability. So given that the null is true, and this is our sampling distribution, how often would we expect to get a sample mean below this? And that would be equivalent to the probability that our z-score is less than negative 2.4, given that the null is true, because that was the z-score known as the test statistic associated with our particular sample mean. So what we'd like to know is, hey, how often do you get a z-score more than 2.4 standard deviations away from the mean? Well, that's where we can use the normal CDF to find how often, what's the probability, what is this probability that this happens. We're going to use software, and we can use normal CDF, and I'm going to teach you how to do the tests on the calculator a little bit later. But it turns out this probability down here is 0.008. And we're going to call that a p-value. We'll talk about it here in just a second. So what we're saying is, we got a result. Our sample mean was so extreme that given that the null would have been true, we should only be getting a result at least that extreme only like 8 out of every 1,000 samples. So it's very extreme, so that p-value helps us assign a probability that we're right or wrong. If the null were true, this should only happen 0.8% of the time, and so we're pretty confident to go with the alternative. Let's go to the next screen, And let's formalize this even further. We need an alpha level, a significance level for the test. Now first let's look at this. Let's suppose these are the test conclusions. We either stick with the null or reject the null and go with the alternative. And let's suppose this is reality. Now what we're concerned with is this. If we end up rejecting the null because we got a small p-value, like in our case our p-value was 0.008, there exists a possibility that even though we got a small p-value, in reality the null could be true. In other words, it is feasible, it is at least somewhat possible that the mean was 44 and we just got one of those really unusually low sample means that should only happen about 0.008 of the time. So if that's true, if that was the case, that man, we got an extreme result, we thought it was a no-brainer that the true mean was less than 44, but maybe we find out 2 years later that the null was true, the mean really was 44, you just got really unlucky and your sample was one of those extreme results. Well, you just made a type 1 error. So this is the probability of making a type 1 error. So it's kind of like this. Let's suppose we got that sample mean way down there. It has this p-value. It's a result that should only happen that often when the null is true. We thought we should go with the alternative. So we said, no, we're going to accept the alternative. We're pretty confident. Now we find out that we're wrong. But now follow this. Well, how do you explain it? We were wrong. We got a result that was really extreme. Well, it just happened due to random chance. You got unlucky. But what's the probability that it happened due to random chance? It's that. So that's the probability of us being wrong if we go with the alternative. That's the probability of making a type 1 error. The p-value is the probability of making a type 1 error. So one more time, got a really extreme result, got a small p-value. We thought the alternative was true. We found out later the alternative wasn't true. The null was true. Dang, we made a type 1 error. But how do you explain that we got a result that extreme? Sorry, just due to random chance. But what's the likelihood it happened due to random chance and the mean was really 44? It happens that portion of the time. So that's the probability that we were wrong. That's the probability of making a type 1 error. The significance level of the test, the alpha level, is before you go into the problem, what are you going to set as an acceptable risk of being wrong? What are you going to accept in terms of making a type 1 error? Well, typically what we accept is what I showed on the other screen, that as long as the p-value is 0.05 or less, 0.05 being 1/20th, 1 out of every 20 samples should be down here due to chance. So if you get a p-value that's 0.05 or less, you get a result that should happen like less than 1 out of every 20 samples, so it's extreme. So this would be our alpha level. By default, use 5% if nothing else is given to you. So here it is, you guys. If the p-value is less than or equal to the alpha level, you reject the null and you go with the alternative because the p-value is the probability of a type 1 error and we're willing to live with up to an alpha level's amount of making a type 1 error. If this were a life or death situation, testing a drug or something, you might set the significance level, the alpha level, at 0.01. But even in this case, our p-value was below 0.01, so we'd still reject the null. That's how that works. Now, it's kind of like in a court of law. Either you're guilty or not guilty. So if we're in the critical region, that's enough evidence beyond a reasonable doubt being the alpha level, like 0.05 usually. So if it's extreme enough, you are guilty. We reject the null. But just like in a court of law, they don't say guilty and innocent because there might be some doubt that maybe they're truly innocent. So they just say guilty and we failed to suggest that you were guilty. We're saying you're not guilty. Well, that's what's happening here. If we take a sample and our sample means below the 44, but it's not past that 1.645 standard deviation critical value, then there's not enough evidence to convict. We failed to reject the null. So get used to that lingo. Now, what if a different company came along? Company B, sample size of 36, they had a sample mean of 43.3. That turns out to fail to get into the critical region. The z-score for that one, if you did the 43.3 minus the 44 divided by the original standard deviation over the square root of the sample size, that would give you a test statistic, learn the terminology, a z-score of negative 1.4. And the probability of being beyond negative 1.4 standard deviations is about 0.08. That's our p-value. We didn't make it down to 0.05. We're not in the critical region. Because our p-value is not less than 0.05, it's not extreme enough. We fail to reject the null. Now, what if somebody instead claims that the new software makes no difference? It's no different than before. Now the claim is that mean is equal to 44. And if you remember, we write down the complement to that. That would be that the mean is not equal to 44. Now, this becomes the alternative. Now, here's what's weird. What would it take to convince us that the mean is not 44? Well, now it could be a result on the left side or a sample mean on the right side, because not equal to means either less than or greater than. This now becomes what's referred to as a two-tailed test, a two-tailed alternative. So if we go back to this example where we got this sample mean with the original company A, then that put us at 42.8. Remember, that gave us a z-score of negative 2.4. We were down here negative 2.4 standard deviations beyond the mean, and we trapped this much on this tail. But that is not our p-value in a two-tailed test, because here's what has to happen. Here's the deal. Before you make your conclusion, you have to continue to assume innocent until proven guilty. Assume the null is true until there's enough evidence to suggest. So we're still assuming the null is true at this sampling distribution. We're just exploring the idea of how unusual was our result. Well, it should happen only 0.008 of the time due to random chance. Hey, if it's just happening due to random chance anyway, and it's tempting us to go with the alternative, then it could have just as likely have been at least 2.4 standard deviations above the mean, which would also have a 0.008 chance of happening. So to calculate the p-value, the null is still true. Assume innocent until proven guilty. Assume that this is true, and just pursue the probability that something like this could happen just due to chance. And it could happen on either side due to chance. So you have to take this probability in one tail and double it. Your official p-value is those two added together, which is 0.016. So on a two-tailed test, you double the probability of getting a result at least as extreme as the one you got on the one tail. But that is still a small enough p-value that if we ran this test at a 5% level, we'd reject the null. And finally, there's three basic kinds of tests. A left-tailed alternative, otherwise known as a left-tailed test, and it's based on the alternative. The null is always going to collapse to mu equals 44 in this case. If the alternative says the mu is less than 44, the only way you can reject the null is to get a sample mean down here. If it's a right-tailed alternative, meaning that the alternative says the mu is greater than 44, now the critical region's on the right tail. Only an extremely high sample mean, well above 44, will cause us to reject the null. A two-tailed alternative or a two-tailed test, you have to have a result. You could have a result on either tail, extreme in either direction, to reject the null. Don't forget, you got to double the area on each side in order for you to get the p-value. I think that's all we need. So there it is, an introduction to hypothesis testing. This test is called a z-test of means because we get to use a normal distribution and we look at test statistics, z-scores, in a normal distribution to help us decide on what our decision will be.